Hi guys, here is my first video for this. I'm gonna be honest with you. I woke up yesterday and I thought I had a sinus thing, but my throat is now pretty sore, and so it kind of hurts to talk. So anyway, let me just show you what the important piece is in this first video, and then I'm gonna rest a little bit, and when I feel better tomorrow or later on today, I'll make a longer, more in detail one. So my idea is this: since this week is kind of short, I want you guys to learn two topics, and it's curl and divergence. And so in this notebook, if you notice down in the lower corner down here, it says we're on page 7 of 16. If I go back to the beginning, this is about Green's theorem, and Green's theorem is cool, and I'm going to explain it, and it'll come next week. And then here is a very easy application using Green's theorem, and here it is what I call the old way, the way that we were originally taught to do it, and then it goes through some other neat things. When we go through that, I'll tell you I do have. Here's the book with a proof and all sorts of things like that in there. So we will go through that as well. And then when we get to finally curl, here is the most important piece for right now. And that's that curl. And so curl captures how a fluid might rotate in there. So I brought up this, and you can see that it says in vector calculus, the curl is a vector operator that describes the infinitesimal circulation of a vector field in three-dimensional Euclidean space. The curl at a point in the field is represented by a vector whose length and direction denote the magnitude and axis of the maximum circulation. And so you can read about it. What does curl and divergence mean? Here's another one. And so divergence means it's either like a pool or a sink, or it's a source, meaning it's where like a spring or something like that. So what we will talk about both of them. So curl, here's what you need to know about curl. Curl, you take a vector field, so this is just a standard vector field right here, and then the curl of that field it's a cross product. And so remember how we do a cross product? We put the ij and k up top, and then this, the partial derivative, partial x, partial y, and partial z goes in that second slot, and then we put the components of the vector field in the last slot. If you work out the curl and that cross product, this is what comes out in there. You can see that if I cross out the y, I get df3 dy, which is right there, and then minus df2 dz, that's right there. When I cross out the j's, I'll get a minus there, and then it should be df3 dx, which is right there, and then df1 dz, which is right there. So all I'm doing is the natural cross product. So usually we write the word curl as the function name, or the operator name in this case, and then the input or the argument of that is the actual vector field. We usually write it like this. We write it as, this is del or nabla, it's called, and so it's like that gradient symbol, but it's del cross f or nabla cross f. And if nabla is partial x, partial y, and partial z, then when you put del cross f, that del should go in that second line, and f should go in that third line. So that's what that is right there. If you took this, and instead of writing it with the I, j, and k vector notation, if you wrote it in angle brackets, that's what shows up down here. So there's a few properties of the curl, and as soon as we define a new object, we want to know what is its properties. And so just like the derivative, we want to know, is curl additive? Like, can we break it up over addition? And this rule here says it is. This is just like d dx of f of x plus g of x is df dx plus dg dx. Or you break it up. And this says, can we pull constants out? And it looks like it does pull out right there. So here is just an example, and all I do in here is follow this very formula right down here at the bottom. So when I keep flipping back and forth, look what we need. We need the derivative of the third function with respect to y. And so in here, there's the third function. There is no y in it, so it should be a 0. Then we have minus, and it should be the derivative of the second function with respect to z. And the second function is y over z. I can write that as yz to the minus 1. And when I take that derivative, it'll be negative yz to the minus 2. And there's that piece right there. And so all you have to do, class, is follow this very formula right here. And you already know how to do every one of those partial derivatives. And you already know what function names are in each slot. And so that is just a quick example of how you would do a curl. And it is so straightforward that I know I didn't finish the whole thing, but all you have to do is go back here, grab that derivative, the derivative of the first one with respect to z. The first one doesn't have any z's, and so it's 0. And so you can just follow through like that. This is a shorthand notation of saying that if the vector field is conservative, so remember, if the vector field is the gradient field of a potential function, then that means the vector field itself is what we call a conservative vector field. And in a conservative vector field, there is no tendency to curl in that. And so that's kind of a cool fact in there. And the reason that it comes, that it's true is because, remember, if a vector field's conservative, it satisfies what we call the cross-partial condition. And so if you subtract these the right way, you can move them all over and get them to be 0. But these pieces are exactly what show up in the way that the curl is defined. And so for that, that's what you need to know right now for the curl. Once you have the curl, then we're going to move to divergence. And so here's what divergence is. Divergence says if f is a vector field, meaning just like this, then the divergence, it's not a vector. Notice this is a scalar. There is no angle braces. There is no cross product in there. There is no I, j, and k vectors in there whatsoever. So divergence is, and it's kind of the most easy thing that you can think of. It is the x derivative of the first piece plus the y derivative of the second piece plus the z derivative of the third piece. And so because we're doing that this way, we can actually think of divergence as del dot f. And to just show you that, here's what it looks like. So del, remember, is partial x, partial y, partial z. And if we dot that with f1, comma, f2, comma, f3, remember the way we do a dot product is the first times the first. Well, how do you do partial of x with respect to f1? Well, that should be the partial of f1 with respect to x. Plus then, because we're doing a dot product, we're going to do the second one times the second one, and that should be partial f2 with respect to y. And then finally, we do the last times the last, and that should be partial of f3 with respect to z. And that is exactly what is written up there. Again, just like with everything else, with the gradient, with partial derivatives, with curl and divergence, all of them, they're kind of like derivatives. And as such, we want to know that they follow the linearity rule. These two rules means that this is what's called a linear operator. So if you have two vector fields, does divergence of a sum equate to the sum of the divergences? And that is true. So if you have two vector fields added together and you wanted to know the divergence of that resultant vector field, you could actually just take the divergence of each vector field and add them together, and that would come out to be the divergence of the actual summed vector field. The second property just says that constants can still pull out, and that is still true. And so in this case, here is an example here. So F is the vector field sine x plus zi. There is no j, and then we have some k in there. And so F does look like this, and I put the 0 in that slot. I like it like written with the angle braces because then I can just look and say, oh, I need that x derivative. Well, derivative of sine of anything is cosine of that thing, and then times the derivative of the stuff inside with respect to x. We're doing it with respect to x. The derivative of x is 1, and the derivative of z is 0. And so we just get cosine x plus z. Then we need the y derivative of the second piece. Well, the derivative of 0 is 0. And then finally, we need the z derivative of the last term. Well, the negative y is going to stay because it's a constant. And derivative of e to something is e to that thing times the derivative of that thing. And when you take the derivative of xz with respect to z, you're going to get an x out of there. And so that's why the x pops. It pops from the chain rule of this by taking the z derivative. And that's all that I want you to know for right now. If you want to go through these notes, like I said in my write-up, there are 3 theorems, and they're here very clearly laid out. One of them is Green's theorem. And Green's theorem is very useful. What Green's theorem does, I'll just tell you now since we have a little bit more time, but this is coming next week, so you don't need to worry about it right now. But if you wanted circulation around some vector field, it turns out that circulation on the boundary can be equated to this double integral of this certain function here. And what that means, and we'll go through the proof when we see it, but I want to show you that if we were going to do this back in the day, as with line integrals and with circulation and all of that, if we had this triangle that went from here out to here and up to here and back to here, that's actually 3 paths, 1, 2, and 3. It doesn't curve where it's just one single loop. It does go out and stops, and then up and stops, and then comes back home and stops. So doing it the old way, we would have to parameterize 3 curves. So one curve here for the bottom, and if you look, t should go from 0 to 1, and the y value is always 0. And if we just let t grow, it'll grow us right out to that point right there. The second one, the x value is always 1 in that case, so you can see 1's right there. And then to run straight up, I just start y at 0 and let y grow all the way till we hit 1. And so putting the t in that y spot, there we have that. And then this one is the line y equal x. And on y equal x, the point is xx, or I can make it tt. And then I'm going to take t from 0 to 1. Now, the problem with that is when I put in 0, I'm going to start at 0, 0. And when I finish at 1, I'm going to go from 0, 0 to 1, 1. And that takes me that direction. That's the wrong way. So I have the wrong orientation. And so in order to fix it, I'm going to put a negative in front of that piece. So it should be the first path plus the second path plus the third path, but the third path has the wrong orientation, so that plus gets offset by a minus. Notice this takes 3 pieces, but in all of these, I'm just doing f of c of t dotted with c prime of t, and then I'm using the limits for t to become my limits of integration. And that's how you would do it the old way, and it would take 3 pieces. But because this boundary right here, and we haven't talked about it yet, it's written up here, but this boundary of this domain is kind of the border, it's the fence, and the fence sucked because the fence was 3 separate pieces that walked around. But this region, if I think of it as just a patch, it's just one region, and it's real easy to describe in terms of these limits here. And so what Green's theorem says is, instead of doing that across the whole boundary, just do a double integral over the actual domain itself, and this will fix the fact that we've switched everything out. And so when I switch this, you can see I went y and then x. So y goes from 0 to x in that case. And then x gets the full gamut. It runs from 0 to 1. And so that's how I got those right there. When you come over here and we talk about Stokes' theorem is a very similar thing down here. Stokes' theorem says if you want a vector line integral, circulation, remember, if the vector field's conservative, this is going to be 0. But if the vector field's conservative, I already told you that the curl is 0. And so if the curl is 0, then we would just be integrating 0, and this would come out to be 0 also. So this, though, needs an orientation, but it turns out that you can trade this out for something a little simpler in certain cases. Again, on this then, and we'll do this next time, but when I go through it, we have this plane, and this plane is in that first octant. And in order to do that the old way, I would need 3 paths, and I would have to parameterize each one of those paths. And then I would need to do f of those paths. And I would need to find the tangent vector for those paths. Then I need to do f of c dotted with c prime for all of those paths. And then I have to set up multiple integrals to add that stuff together. The new way, though, using Stokes' theorem, says trade this out, which may be long and drawn out, for this thing right here. And you just need to compute the curl and then use the actual surface itself in that double integral. And so in doing that, you can see down here, we got the exact same thing. And then the final theorem in here is the theorem for divergence. And it says if you want the surface integral, you can trade it out for a triple integral of the divergence instead. And so sometimes encoding this is hard because you have to parameterize the surface. Notice this is a parameterized surface. And so you have to parameterize it. And unless it's like a sphere or a cylinder or something that is fairly simple, this could get complex. Also, if you guys did the homework that's due tonight and you looked at number 15, I will tell you, multiple people came to office hours and asked about number 15 because number 15 goes over a cube. And because you're going over a cube, the cube has 6 faces. You have to do 6 separate surface integrals. And on that, you need to do one for each face. That's if you did it this way. But using the divergence theorem, you can trade it out for a triple integral of the divergence. And encoding this cube, You just have like 0 to 2 and 1 to 4 and 3 to 6 or whatever, however the cube runs. And so this turns out to be very, very easy. And so anyway, we will talk about that. But for this week, what you need to know is, how do you do divergence? Divergence is a scalar. And I wrote this in my write-up. The divergence is a scalar. You can see it comes out to just be 3 partial derivatives added together. But curl turns out to be an actual vector, and it's because curl is defined as a cross product. So curl is a vector and divergence is a scalar. That's one important thing to note. And for this week, you're going to read a little bit about it and look at it, and ultimately, you're going to get good at computing it. And then next week, we're going to take circulation integrals, line integrals, and surface integrals, and we're going to trade them out using Green's theorem, Stokes' theorem, and the divergence theorem to make life easier for us. So I'm going to stop there. That should be enough to get you guys through the homework this week. You have the textbook. You have both sections. I laid them out for you. You can read those also. You can read through my notes. You can watch this video. You can find other videos. And there's a discussion where you can ask each other in class if you have questions. Don't worry about the 3 big player theorems right now: Green's theorem, divergence, and Stokes' theorem. Those we will talk about next week. For this week, just enjoy your family, enjoy Thanksgiving, and be safe. But make sure you know how to do the curl and how to compute divergence, and be ready to use them next week. All right? Take care, you guys. Bye-bye.